Okay, so this is our presentation on the new concepts of thermal management system in lithium-ion batteries using air cooling as well as heat pipes for electric vehicles, our update slides. So I am Ryan Wirt.
Matthew Warner.
And I'm Peter Woodruff.
Okay, so first we're going to go into talking about forced convection. And so this is just a YZ plane side view of an early run of the thermal batteries in the container. And so what we're doing is we're just showing how the airflow flowing from left to right can change in temperature. So obviously at the left, you've got the input of 20 degrees Celsius. And on the right, we can see that that airflow has jumped all the way up to like 29 degrees Celsius. And then, as you can see, it's a very small structure. It's only 130 millimeters across. And then moving on to the next slide, this is now the XY plane view. And we have two different ones. One is at 20 millimeters, so it's closer to the front. And then the other one is at 70 millimeters. It's kind of hard to tell, but if you do look, you can see how the one at 20 millimeters on the right does have slightly lower temperatures than the one on the left, which just shows how as the air heats up going throughout it, it has less and less effect on the thermal properties of the batteries and their overall temperature. And then so for next steps for forced convection, if you read the temperature ranges on those screenshots, you could see that they were about 293 degrees Celsius, which obviously is much higher than what we are aiming for. So now just for the next couple of weeks, next week, the goal will be to kind of try and lower those to more realistic, 40, 50 degrees Celsius ranges of what we're looking for.
So yeah, this is the heat pipe. I'm attempting to model the heat pipe here. Here's the nodes and elements. You can see in the figure it operates horizontally, or it looks horizontally, but in the experiment it operates vertically, so gravity is a factor. Next slide. So this is the setup. I'm taking it pretty simply right now just to try and get some good results and to move on to more complicated, more accurate stuff once I get that. So I'm setting it up where I have a heating element on the bottom in the evaporator section, and I have a cooling, a locked temperature of 290 Kelvin on the top in the condensing section, sort of to model a boiling element. Next slide. So these are the volume fraction contours that I was able to achieve. I was able to do some boiling, so I actually got some decent results here. So on the left side, you can see the volume fraction of water. So it's mostly water there, but you can see in the two pictures that some of the water had turned into steam there. So there was actually a little bit of boiling going on in that picture. Next slide. So a lot of limitations for this that I couldn't model the heat pipe like the one exactly in the research paper. So the wick structure, it's difficult to model a wick structure. Just trying to model a porous element for the liquid to flow through. That was very difficult to do. I don't know if that's even possible. Also, another limitation is that in the research paper, the heat pipe is divided into two sections where the liquid is only in the wick and the vapor section is only in the actual pipe. And I was having difficulty doing that. I'm not sure if that's possible to do either. Next slide. Just some next steps for the heat pipe is to obtain a model that resembles the study closer. So find some better temperature contours and then replicate the heating and cooling elements. So do a more accurate examination of that and more accurate inputs and outputs from that. Next slide.
So for the MATLAB code, the original goal was to find the outlet temperature of the heat pipe given the certain properties of that were given. Now, in order to find a range of the outlet temperatures, we assumed 10 to 60 watts for the heat transfer rate. And this would give us a good starting point to see how the different wick structures would affect the outlet temperature. So for the first assumption, or for the first test, we assumed the porosity was at 95%. This gave us a resistance total that was close to the published results, which was 0.202. And so you could see that the wrapped screen, packed sphere, and sintered fiber are relatively close to that, and that was for 95%. The next step, next slide. The next, so we see here that 55 watts would be the optimal heat transfer to get what was desired to be 37.5 degrees Celsius. And this was true for all of the different wick structures. You could see here that at 50 watts, the outlet temperatures was 37.21, 37.43, and 37.27, which were all very close to the desired. Now for the next slide. Now for the next step that I did was I changed the porosity for the wrap screen and the packed sphere to be 60%, and which gave us a lower heat transfer rate needed to get the higher temperature. It was about 30 to 35 watts was the best that could be done at that moment. And for figure 7A, I kept the sintered fiber at 95% to show the difference between the two. And for figure 7B, I chose 60% porosity for all of the wick structures, and all of them are relatively close to 30 to 35. The sintered fiber was closer to 35 to 40 watts. So for the next step, I'd like to add a range of porosity from about 50% to 90% to see how that also would affect the outlet temperatures, and hopefully gets us a lower heat transfer for the higher temperature. Thank you.